Hi everyone, let's talk about sessions 4.6, the mean value theorem. Big idea. For any differentiable function on a closed interval, there will always be a point in the interval where the derivative of the function equals to the slope of the line between the endpoints. Big skills, you should be able to verify the conclusion of the mean value theorem for any given points, and to prove the results about the number of zeros of a functions together with the intermediate value theorem. So we learned intermediate value theorem in sessions 2.6. Today, we're going to combine the intermediate value theorem and the mean value theorem to talk about the number of zeros of a function. Okay, so let's review what other theorems we learned. We learned extreme value theorem. What's extreme value theorem about? It says if f is continuous on a closed interval, so we have continuous on a closed interval AB, then f attains an absolute maximum value f of c, and an absolute minimum value f of d at some numbers c and d in the interval. For example, because it's on the closed interval AB, so if our picture is like that, well, then we're gonna have a absolute maximum at c, and here we can have an absolute minimum at d. Right? So it might happen that we have several absolute maximum and several absolute minimum. That's possible, okay? But we must have at least absolute maximum and at least one absolute minimum on a closed interval AB. Okay. Second, we have the local extreme point theorem. If f has a local maximum or minimum, then if the derivative exists, the derivative must be 0. So it tells like that. If we have a local maximum or minimum at c, okay, the derivative is 0 at c, okay, so it's either the derivative exists, then the derivative is 0, okay, or the derivative does not exist. So the picture could be something like that. At this guy, the derivative does not exist, but we also have a local maximum there. Okay, so you can say this theorem is about if f has a local maximum or minimum at c, then either f prime of c is 0 or f prime of c does not exist. Okay? And let's talk about the intermediate value theorem. We learned this in session 2.6. Suppose f is a continuous function on an interval a to b, and L is a number between f of a and f of b. Then there is at least one number c in AB satisfying f of c equal to L. Okay, and this is a picture. Remember, you're standing here, your girlfriend is standing across the street. How do you find your girlfriend? You must cross the street, right? You cannot jump to your girlfriend. We must cross the street. So you might cross your street once at C, or you might cross the street a couple times. So far, so good. Or you can, the picture, it could be like that. Then actually we have infinitely many C such that f of c equals to L. Okay, so in order to use the intermediate value theorem, okay, you're gonna verify the hypothesis of the theorem, and then we can draw a conclusion, right? The hypothesis is, first, f is continuous. Okay, second, L is a number between f of a and f of b. So usually if we want to show a function has a root, then the L is the 0. That's why you want to pick a number such that f of a is positive, and you want to pick another number b such that f of b is negative. Okay, then we can draw a conclusion. So here are the conclusion. Okay, then there are at least one number C such that f of C equals to L. Okay, so we have two hypotheses and we have a conclusion. Okay, so next is something new today. The Rolle's theorem is also called the Raleigh's theorem. Let f be a function that satisfies the following three hypotheses. Okay, so first hypothesis. A is continuous on a closed interval AB. So continuous. Second, f is differentiable on the open interval AB. So differentiable on the open interval, the interior of the closed interval. 3, we require f of A equals to f of B. Then the conclusion. There is a number C in AB such that f prime of C equals to 0. Okay, so let's look at the first picture. So this is you can see f of A equals f of B. Actually, this is a constant function, so all the numbers in between, we have the derivative is 0. The slope is 0 at those points. Okay, the second picture. So you can see here we have 1 point such that the slope at that point is 0. Okay? And this is always true because here the function is differentiable, so we can only have like this. So we always have some points that the derivative is 0. So we're not allowed to have this case because this case the derivative does not exist. Okay, so we don't have this case. Alright, and next one, this guy, you can see the C is here, and here A and B, and here we have two C values. So far so good, everybody? Okay. Let's work on example 1. Prove that an equation has exactly one real root. Okay, so how do we do it? Has exactly real roots. Exactly one real root. Exactly one real root. Okay, it means we can separate into two steps. Okay, so we can prove it has at least one real root. So at least one real root, and we can also show it has at most one real root. Then when we combine together, we get exactly one real root. So for at least one real root, we can use the intermediate value theorem. For at most one real root, we can use the Rolle's theorem. And we can also use the mean value theorem. So we'll talk about later. But the Rolle's theorem is just a special case of the mean values theorem. Okay, so here are the steps. First step, we want to define our function. So we define our function to be the left-hand side minus the right-hand side. Okay, so to solve this kind of problem, like showing a equation has exactly one root, the steps are almost like the same. So here I'm gonna use green color to denote that something new. When you see a new different function, you just need to change the green part. The black parts stay the same. Okay, so the left hand side in our problem is x to the 5th plus 7x. The right hand side is 2, so we subtract 2. So far so good. We use the left hand side minus the right hand side. That's the first step. Well, second step, we want to show at least one root. How do we show it? Use intermediate value theorem. Okay, so you need to verify the hypothesis of the intermediate value theorem. Okay, so the first one is f is continuous. Well, is it continuous? Because here it didn't give us an interval, so we assume that we want to prove the equation has exactly one root for all real numbers. So first, f is a polynomial, so it's continuous everywhere. Okay, so we say it's continuous. And second, let me just use the dot to denote. Second, we want to find a point A such that f of A is positive, and we want to find a point B such that f of the point B is negative. Well, here usually the number we plug in is we can try the 0. So when we plug in 0, you can see we get -2, so it's negative. And the other numbers you can try 1, -1, 2, -2, 10, -10. You can plug in any number. So in this case, let's plug in 1. So when we plug in 1, so let's write more. Oh, okay. So I should use the green color for it because a different problem this might change. So here we plug in 1. We get 1 plus 7 minus 2. That is 6. So 6 is positive. Okay, and next we plug in 0, and then we get -2. -2 is negative. Okay, so we find a number such that f of that number is positive, and we find another number such that f of that number is negative. Okay, so that is the hypothesis of the intermediate value theorem. Then we can say then by the intermediate value theorem, there is C such that f of C equals to 0. Okay, so that's why IE equation has at least one root. Okay, so that is step 2. And then next we have step 3. Step 3, okay. We have we want to show at most one root. Okay, so we want to check the hypothesis of the Rolle's theorem. First, we need f is continuous, and it is. Yes, it is. It's a polynomial, so it's continuous. And second, we need f is differentiable. Is it? Let's differentiate. Well, when we differentiate, we get 5x to the... Oops, so this is special to this problem. So let's use green. Okay, so we have 5x to the 4th. And then plus 7, right? And you can see x to the 4th is always greater or equal to 0. So when you add 7, this guy is always positive. All right. And then what's next? This guy is always positive. So next we want to, okay. So next we want to show at most one roots. So here we're gonna prove by contradiction. Okay, so next we're gonna prove by contradiction. So what is proof by contradiction? That is, you assume your hypothesis is wrong, and then you continue, and then eventually you get a contradiction. That means whatever you assume is wrong. So that's why here. Okay, so let's assume that at most one root is wrong. So okay, that means suppose we have two roots. Suppose A, B are roots. What does that mean? It means f of A equals f of B equals to 0, right? They're both roots. Okay, so we suppose there are two roots. That is like the negation of at most one roots. Okay, so if we have two roots, f of a equals f of b is 0, then because f is continuous and f is differentiable and f of a equals f of b equals 0, so those are all the hypotheses of the Rolle's theorem. And then say by the Rolle's theorem, there is a C such that f prime of C equals to 0. But what happened? Our f prime of x is positive for all x. This is a contradiction. Okay, so contradicting the fact that f prime of x is positive for all x. And because we have a contradiction, it means whatever we assume is wrong. So we cannot assume there are two roots. There can be two roots. So that means there is at most one root. So far so good, everybody. So combine all together, we get thus the equation has exactly one root. Okay, so combine all these, we get the equation has exactly one root. And you can see for a different problem, the different equations, the steps are almost the same, and we only need to change the green parts. And there are only 4 green parts there. Okay? Alright, so I hope that you can pause here and try to work on example 2. Are you done? Let's check our answer. So first, define f of x. F of x is the left-hand side minus the right-hand side. Okay, that's the first step. Second step, you want to show at least one root. Okay, so we check the hypothesis. First, f is continuous. Second, we want to put some points. Usually the point we plug is 0. When we plug in 0, 2 e to the 0 is 1, and 5 times 0 is 0, minus cosine 0 is 1. Oh, so this guy is positive. Next, we need to find a negative number. Okay, what negative number? Let's plug in. We need a negative number. Let's try to plug in minus 2. Let's see whether it works. Okay, so when we plug in minus 2, we get 2 e to the 3 times minus 2 is negative 6. Minus 2 times 5 minus 10. Minus cosine of negative 2. Well, but you know, negative cosine is always bounded between minus 1 and 1. So this is small. And you know, exponential function when t is negative is actually less than 1. So this guy is less than 1. So that's why here this guy must be negative. Well, you can also put this in your calculator, and then you will see the answer is negative. Okay, good. So we have verified all the hypotheses of the intermediate value theorem. So by intermediate value theorem, there is a C such that f of C equal to 0. So i.e. equation has at least one root. Okay, and then 3, we want to show at most one root. And what are the hypotheses? We need f is continuous. It is exponential function, cosine, polynomial are continuous. We need f is differentiable. Well, let's differentiate it. So that is the derivative of 2e to the 3x. 3 times 2 is 6. 6e to the 3x. The derivative of 5x is 5. The derivative of negative cosine is negative sine. So negative become positive sine x. Okay, what is this? Well, you know the exponential function is always positive, right? And the sine is between -1 to 1. Well, this guy at 5, this is always positive. Okay, so this guy is always positive. All right, so that's why so you either get always positive or always negative. That's always the case, because later on we want to show we have contradiction to f prime of c equal to 0 for some c. So in order to get contradiction, this guy is, you get either always positive or always negative. All right. Okay, so proof by contradiction. Okay, so suppose we don't have at most one root. Suppose we have at least two roots, right? So suppose a, b are roots. Then f of a equals f of b equals to 0. Then we satisfy the three conditions of the Rolle's theorem. So by Rolle's theorem, there is c such that, actually the c is between a and b. Okay, such that f prime of c equals to, the L is 0. But this is contradicting the fact that f prime of x is positive for all x. Because we get a contradiction, so whatever we assume is wrong. We cannot have two roots. So that's why equation has at most one root. Okay, and all combined together, thus the equation has exactly one root. Okay, so that finished the problem. You can see the process are very similar to our previous problem, just the green parts change. Okay? All right. Next, let's talk about the mean value theorem. Okay, so I mentioned before the Rolle's theorem is just a special case of the mean value theorem. So let's look at the mean value theorem. Let f be a function that satisfies the following hypothesis. First, f is continuous on a closed interval ab. Second, f is differentiable on an open interval, the interior of the AB. Okay, so open interval AB. So here we actually only have two hypotheses. Okay, then the conclusion is there is a number c such that f prime of c equals to the slope of the secant line passing through the two endpoints. You can see here, this is the two endpoints. This is the two endpoints. And this guy is the secant line passing through the two endpoints. Okay, so this theorem tells us that if f is continuous and differentiable, there must be some point such that the tangent line at that point has the same slope as the secant line passing through the endpoint. Or we might have like 2 points such that the tangent line at those points, the slopes are the same as the slope of the secant line passing through the endpoints. Okay, so this is the slope of the secant. Oops. The secant line. So why the Rolle's theorem is a special case of a mean value theorem. So if you can remember the Rolle's theorem. Okay, so the Rolle's theorem, we actually have the condition 1 and 2. We have one more condition. We require f of a equals to f of b equals to 0. So then you can see if we know this information, when we plug in here, we get f prime of c equals to f of b equals to f of a. So our numerator is 0. So because our numerator is 0, so this is 0. So that's why the Rolle theorem, we have an extra condition about f of a equals to f of b that will make that f prime of c equals to 0. Okay? Next, zero derivative implies constant function. So if f is differentiable and the derivative is 0 for all x in the interval ab, then f is constant on the interval ab. Does that make sense? So the slope is 0. The slope is 0, so it means it's like that. The slope is 0, and then so this is a constant function. But be careful, you have to restrict it on an interval AB. So here, the AB, it could be minus infinity to infinity. Then the function is a constant function, all real numbers. But we're gonna be careful. To be careful, it must be an interval. It cannot be like a union of two distinct interval. Okay, so gotta be careful. So be careful. It can't be a union of two disjoint interval. For example, let's look at this picture. So we have 0, we have -1, we have 1. Okay, so I defined my function to be, okay, -1 here, and I define my function to be 1 here. So you can see this function is defined from -1 to 0 and from 0 to 1. So it's not a one piece of the interval. It's like a union of two subintervals. Okay, and you can see the derivative. Let's call this guy g. G prime is all 0. It's all 0 on the domain. But however, is this a constant function? No, this is not a constant function. It equals different constants. Okay, so that's why the zero derivatives implies constant function. We have to emphasize is on an interval AB. Okay, it cannot be like a union of two subintervals, disjoint intervals. Okay, so we have to be careful with that. Next, functions with equal derivatives differ by constants. So if two functions f and g, they have the same derivative for all x in an interval ab, then f minus g is a constant on the interval ab. So how do we prove it? Well, you just define. So you can define a new function h to be f minus g. Then we get h prime is 0 on the whole interval ab. So that's why h is a constant function on the interval ab. So that means f minus g is a constant. F equals to g plus the constant. Okay. We marked. Care must be taken in applying this theorem. For example, here, so let's look at this picture. So is 1 when x is greater than 1. Oh, and it's minus 1 when x is less than 0. Okay, so this is just like what I just said. Okay, you can see the domain is everything except 0. Okay, and the derivative is 0 for all x, but this is not a constant function. It does not contradict the theorem because the domain is not an interval. It's like a union of two intervals. Okay. Alright, so it's time to work on our example 3, okay? So, example 3, determine whether the function satisfies the conditions of the mean value theorem on the interval from -2 to 2. If so, find the points guaranteed to exist by the theorem. Okay, so let's work on this problem. Okay, so what do we do next? We first want to check it satisfies the mean value theorem, right? So what are the conditions of the mean value theorem? First, is f continuous? Yes, f is a polynomial. Polynomial is continuous everywhere. Second, is f differentiable? Well, let's take the derivative. Does that exist everywhere? Okay, the derivative is 6x squared minus 3. Well, this guy exists everywhere, so f is differentiable everywhere. And so we know that it satisfies the conditions of the mean value theorem. And then by mean value theorem, there is a c on the interval -2 to 2, such that so in the interval such that f prime of c equals to f of the final endpoints 2 minus f of the initial endpoint, and then 2 minus -2, right? So what is that? Well, f of 2, that means you plug in the 2 into our original function f, right? So we plug in the 2 there, so we have 2. Okay, so we're looking at this. 2 times 2 cubed is 8. 3 times 2 plus 1. And then we subtract this guy. So this guy is, we plug in -2 there. So -2 cubed is -8. -2 times -3 is positive 6, right? And then we have plus 1. Okay, now let's see what happened. And the bottom 2 minus -2 is 4. So here you can see the 1 cancel. Okay, so let's see what's the top. So we have 16 minus 6 minus -16 becomes 16, and then minus 6 again. So that is like 10, then another 10. That's 20 over 4, which is 5. Okay, so that is 5. Okay, so we want to find a c such that f prime of c equals to 5. But what's f prime of c? Well, we plug c into our derivative. So f prime of c equals to 6. We plug in x equals to c. So 6c squared minus 3 equals to 5. So 6c squared equals to, we add 3 on both sides. We get 8. C squared is 8 over 6. That is for third, right? So c is plus or minus square root of 4/3. That is square root of 4 is 2, and then over square root of 3. Okay, so here we are looking for the points. So these are just x values. Because we're looking for the points, we also need to plug in the f to find the y values. Okay, and you may notice that both of them, so both are in the interval -2 and 2. So we consider both of them. Okay, so let's see. F of 2 over root 3 is, so we have 2. 2 cubed is 8, and then we have 3 over root 3 minus 3 times 2 over root 3 plus 1. So that give us, let's see, that give us, what is that? So 3 over root 3, the common denominator, here we have 60 minus, here we need to multiply extra 3. So 339 times 2, 18, plus 3 over root 3. So what do we get? We get 3 over root 3 minus 2 over 3 over root 3. And then how about when we have an extra negative there? Okay, so when we have an extra negative, the first term becomes negative, right? So minus 16 over 3 root 3, and the second term become positive. So that is 6 over root 3, and then we still have plus 1. So we can take the common denominator, negative 16 plus 3 times 6, 18 plus 1, so we have 2, 1 is 3 root 3. So through 2 plus 3 root 3 over 3 root 3. Okay, so finally the points are, c is 2 over root 3, and then the y is 3 root 3 minus 2 over 3 root 3. The second point, where the c equals negative 2 over root 3, and then my y is 2 plus 3 root 3 over 3 root 3. So we have 2 points satisfied. Okay, everybody? So that is example 3. Okay, so in the problems in this sessions, I either ask you to give you an equation, and then you're going to show me the equation has exactly one root. Okay, the second type of problem is like this. You give you a function, you're going to show the function satisfy the conditions of the mean value theorem, and then you can find the points guaranteed to exist by the theorem. Okay. And next, so we have another type of function, a problem. Do you still remember in chapter 2, I give you a piecewise function and ask you to find a k such that the piecewise function is continuous. So here is like the upgrade version of that. I give you a piecewise function and give you some parameters a and b. You're gonna tell me what values of a and b such that the function is continuous. And you also need to tell me what values of a and b such that the function is differentiable. Okay, so let's try to work on these problems. So this is our function. F is a piecewise function. It has 2 pieces. Okay, so part A, for what values of a, b is f is continuous at 0. Okay, so this is similar to what we have done before in chapter 2. So we compute the left-sided limits of the function at 0, and we compute the right-sided limits of the function at 0. So the left-sided limit is this piece, right? So we use that formula, which is 5x e to the 2x plus 4 minus a. Okay. So we plug in x equal to 0. So we have the first term is 0. Then we have 4 minus a. Right, everybody? And next, we compute the right side limit. The right side limit, the formula is a sine 3x plus b. And when we plug in 0, we get what? Sine of 0 is 0. And we just get b. And don't forget, some of you lose the points. Where is the equal sign? There. So this is f of 0. We have to mention it. Okay, because in order to have a function continuous, we need the left side limit equal to the right side limit, so the limits at that point exist. And we also require the limits at that point equals to the function value at that point. So that's why this is so important. So, and then we set them equal. That's why if 4 minus a equals to b, that means a plus b is 4. So we say if a plus b equals to 4, then f is continuous. F is continuous everywhere, right? Because f is continuous on those two pieces. Now we make sure the two pieces agree, so we won't have like the picture of this. This is a jump discontinuity. We make sure those two pieces agree, so then f is continuous everywhere. Okay, that's part A. So that's what we have done before. Okay, so part B is something new. So we want to find what values of a and b is the function differentiable. Differentiable, then instead of looking at the function value, we want to look at the derivative. And we want to make sure the right derivative equals to the left derivative. What is the left derivative? Well, that's the first piece. So we take the derivative of the first piece. Okay, and the second one, we want to take the derivative of the second piece. Okay, now let's see. When we differentiate, can you see this guy? We have product. So we have product rule. Okay, so what is product rule? Product rule is the first guy prime times second guy plus first guy times second guy prime, right? And then derivative of 4 is 0 because it's a constant term. Derivative of a, is it minus 1? No, a is just a number. Okay, a is a constant. So we get zeros for those. Okay, and then let's continue. So we have continue. We have the limit. X goes to 0. Derivative of 5x is 5 e to the 2x. And then we have 5x. Derivative of e to the 2x is 2 e to the 2x. Okay, so now we plug in 0. We see the first e to the 0 is 1, so we have 5. But the second term, because of the x, when we plug in x is 0, is all gone. Yay. Okay, so the answer is 5. How about on the other side? On the other side, so here a is a constant. Don't use product rule here. This is not a product. So a is constant, multiple is stay the same here. Derivative of sine is cosine. But because of the chain rule, you have an extra factor of the 3. And then derivative of b is just a number. Derivative of a constant is 0. Okay, so now you plug in x is 0, so cosine 0 is 1, so we have 3a here. Okay, so as long as the left side derivative and the right side derivative equal, then we have the function differentiable. Okay, so set them equal. So we have 3a equals to 5. A is 5 over 3. Are we done? No, because to be differentiable, the function has to be continuous first. Okay, so that's why we need to combine the condition we get from part A. So from part A, okay, so from A plus B equals to 4. Okay, so now A is 5/3. Then B is 4 minus 5/3. The common denominator is 3. Then we have 12 minus 5. So 7/3. Finally, we say if A is 5/3 and B is 7/3, then F is differentiable everywhere. So far, so good, everybody? So, let me just write down, what is that? Okay, so, differentiable implies continuous, okay? And not continuous implies not differentiable. Okay, so in order to be differentiable, the function has to be continuous first, because if it's not continuous, then it's not differentiable. That's why we still need to combine the condition we get from part A. Okay, so I will give you more exercise, and then you can work on this type of problems. Okay, have a good day. Bye.